the picture, then it disappeared.
Okay, I think we're ready to start. I want to thank, first of all, Laurent for being with us, Laurent Freidel from Perimeter Institute. Despite the not so favorable circumstances. So today the seminar will be slightly different than the usual format. It will be a bit longer because Laurent has prepared a presentation that is relevant to, very relevant to trying to create common focus points between the two communities of quantum gravity and quantum information. We might, as we discussed, make a small pause somewhere in the middle to discuss. If you have short questions for clarifications, feel free to write in the chat or raise your hand. And yeah, Laura, whenever you're ready.
Right. Thank you, Marius. So I'm really grateful to be here, to be part of this big KISS family. And I thank the organizer for giving me the flexibility to postpone the talk. And I'm sorry we had to do that. So today I want to talk about, the nature of quantum entanglements of space and in the context of gravity. And as you'll see, this is really a tale about Noether theorems and the notion of gravitational subsystems. And I'll take an historical perspective on that. It's a reflection, it's a tale about the collections of work I've been doing in the past 5 years with many collaborators. I've been blessed with many talented collaborators, which are listed here. So the one question, the fundamental questions that really I'm interested in, and I'm not the only one, of course, which is just one of the central questions of quantum gravity, is what are really the fundamental quantum gravity degrees of freedom? In a concrete manner, these questions, is often posed as in the context of black hole physics, where the area of the black hole horizon stands for an entropy. But this is originally a geometrical quantity, so there's this fundamental question of what is this geometrical entropy counting. Now, in the past, what has happened is that people have made Planckian guesses about what the answers to these questions is. So, people have postulated that these are strings or loops or causal sets or branes or non-commutative geometry. And that's not what I want to do here. What I want to do here is really start from the information about the notion of symmetry, the notion of space that we have available to us in the semi-classical theory, and build up the foundations of quantum gravity from there, and then try to recognize what elements we have from that perspective, from these different approaches. And this means that we're taking a new perspective on the quantum gravity problems. And taking a new perspective, for me, really means asking new fundamental questions. And the central questions that I've been asking, and with me, many others, is really, what is the nature of entanglement across subregions of space, so subregions of space-time. And it turns out, and that's what I'm going to try to explain, that this question is in fact associated, that's not completely obvious, but this is really what it is about, that these questions of the nature of entanglement is really associated with another fundamental question, which is, what is the symmetry of gravity? What is the symmetry of fundamental physics? Now, understanding these questions mean that we had to develop new tools, which are covariant phase space, coadjuvant orbit, representations of sphere loop groups, and I'm not going to talk about that. But conceptually, it also means that we're following a new principle, which we call a local holography. And to connect to the community here of the KISS community, these ideas there are fundamentally related to the idea that the notion of reference frame in a quantum theory needs to be promoted to a quantum reference frame, and we need to leave the notion of classical reference frame as label sets for how we label events in space-time. And understanding this notion of the quantum reference frame of space-time is kind of related to understanding what is the nature of the quantum degrees of freedom. So I hope I'll be able to explain this. Now, I mentioned this word of local holography, and what I want to present is that this notion of holography in general is simply results simply from developing a deeper understanding of the Noether theorem for gravity theories. And this means that, it implies developing an algebraic picture of space-time geometry and its entanglement. And of course, the basic setup we are focused on is that it's a very elementary setup. If you want to understand, let's say, what's inside a piece of chalk or any piece of matter, what you would do as a naive experimentalist is that you would try to break it open and see what's inside, right? So if you want to understand really what is the nature of space-time degrees of freedom, one operation that you need to be able to understand is what does it take to kind of cut open a piece of space and cut it open in such a way that you understand very precisely what it would take to really glue it back seamlessly. And this seems like a very naive question, but this means, this question is really about understanding the nature of subsystems, what characterize a subsystem. We all often think about space-time as a whole, and here we're trying to break it into little pieces, and hopefully understanding the nature of this breaking and the gluing back gives us enough information to understand what geometry is, what quantum geometry is. Now, I mentioned the word holography. This is a word which is used over and over again. There's different notions of holography. The most famous one is ADS-CFT holography. In this holography, the boundary is asymptotic, time-like. It's rigidly defined by boundary condition. It doesn't allow outgoing radiation, and it means that the system is closed and it's unitary by design. Okay. Another more interesting for me as a quantum gravity notion of holography is celestial holography. In that case, celestial holography focuses on a boundary which is asymptotic and null. It's not defined by a boundary condition, but just by fall-off conditions. And these fall-off conditions allow radiation to exit the system. And it means that the system in that case is open and allow energy loss. So in that case, there is a time dependency in the system. We can consider, black hole formations from this holographic point of view. Now, when I mentioned about local holography is that I want to really bring in this idea of holography into the bulk, if you want, and for finite surfaces. And this is the notion of holography that is needed if you want to understand what it takes to cut open subsystems in gravity. And it requires a choice of Cauchy domains attached to finite corners. And it doesn't, the idea of gluing back seamlessly is that you want to do that without having to impose any boundary condition that somehow breaks the symmetry or reduces the degrees of freedom. And what we are learning in this process is that each holograph is associated with the corresponding symmetry group. Conformal symmetry for ADS-CFT, generalized BMS for CFT, or what I'm going to talk about today, Coronal Symmetry for local holography. So the goal, is to prove that somehow geometry can be recasted and encoded into a set of symmetry charges. So we want to have a correspondence between geometry and symmetry. And the core of this correspondence stems from Noether's second theorem, which can be summarized as follows. Like if you take a slice, like a sigma is a domain of space, it has a boundary S. This boundary S can be viewed as a corner of space-time of a causal diamond attached a space-time, and in this causal diamond you have a time development. And the essence of Noether's second theorem is that for any such decomposition of subsystems here, there's a symmetry charge attached to these operations, and these symmetry charges are not attached to the slice sigma, but they are attached to the corner, the codimension 2 corner. And this codimension 2 corner are already the entangling sphere along which you're going to glue pieces of space. So I'm not assuming that you're familiar maybe with this essence of the Noether theorem. So let me take an historical detour onto this very, very important paper of Emmy Noether that appeared in 1918. So what happened is that, you know, in 1915, almost the same weeks, you know, Einstein proposed the Einstein equations, which were written for the first time. And almost at the same time, David Hilbert proposed a variation principle for them. And then a puzzle that was emphasized by Hilbert and Klein arose about the nature of conservation of energy in general relativity. So conservation of energy was understood to be a central concept of physics. But as Hilbert mentioned here, Hilbert was the first to notice that the conservation laws of classical mechanics that applies to the mechanics of continua, energy momentum theorems, are already contained in the field equations in the new theory initiated by Einstein. They therefore lose their independent importance. And that created a debate and a lot of confusion between, you know, in the field about why is that so? What does that mean that somehow the conservation laws, energy conservation laws becomes trivialized? And this is why Hilbert and Klein invited Noether, who was at the time a mathematician, a specialist in the theory of algebraic invariants, to Göttingen, to help them resolve the puzzle about energy conservation. And in July 1918, she published her famous paper, Invariant Variational Problem article. And this paper is you know, extremely important for physics. It was forgotten for a long while, but it's extremely modern, as I'm going to explain what it contains. So here's the abstract of Noether's paper. And it contains two theorems, right? The abstract says if the first variation of an integral is invariant under a finite continuous group with n essential parameters, then n linear combination of the Lagrangian derivative becomes divergences. In particular, 1/2 of the n first integrals of the differential equation given by the vanishing of the first variation. So this is the theorem that everybody knows, that symmetry leads to conservation laws. And there's as many conservation laws as there's symmetries. So translation in time symmetry gives energy conservation. Now, the second theorem is often not really understood properly. And this is where we're going to dig more into. So the second theorem says that if the first variation is invariant in the infinite continuous symmetry group with n arbitrary functions these times, then there exists among the Lagrangian derivative and their differentials n linear identities so that n equations become a consequences of the other. For both theorems, the converse holds. So what it says there is that it's a formalization of the puzzle of Hilbert, that somehow energy conservation is almost, bulk energy conservation is almost a triviality in the context of generalized theory. And this has far-reaching consequences. And the fact that the converse hold means that somehow you can view that as a deeper expression of the equivalence principle. That is, if you have such a triviality in the conservation of energy, you do have necessarily diffeomorphism invariance. That's the essence of these theorems. And this is, what happens. So here is, what it means. And here, what I'm doing is, I'm sorry for this technical slide, but this is really exactly what the paper of Emmy Noether contained 100 years ago. It's very elaborate. So what did she show? In practice, she showed the following things. She took a Lagrangian L, and she, of course, understood and was the first one to show that the Lagrangian variations gives the equations of motion, which I call EI here, and phi are, let's say, the fields. So the Lagrangians, gives the equations of motion up to a boundary term, and this boundary term is now called the symplectic potential. And if you take a variation of the symplectic potential, you construct the symplectic form, and you integrate that over a slice, you construct the symplectic form, which essentially labels all the degrees of freedom of the theory. And this is somehow the source of quantum mechanics, if you want. Now, if you have an infinitesimal symmetry, it means that the Lagrangian is invariant up to a boundary term here, which is just given by the contraction. So if you have a symmetry labeled by, let's say, xi represents a vector field, so the boundary term is simply the contraction of the Lagrangian along this vector field. And then you get another first theorem, is that the equations of motion contracted with the variation of the field are proportional to a total derivative of the Noether current. And the Noether current is a combination of the symplectic potential contracting along the symmetry and the contracted Lagrangian. Okay, and of course, if the equations of motion vanish, you get that this object is conserved. And this means that the Noether charge is here, is a conserved charge, and it's canonical generator. So I think everybody kind of is used to that part of the theorem. Now, the second theorem goes a little bit deeper than that. It says that if you have an infinite dimensional symmetries, then which are labeled by n functions instead of just n vectors, then there exist n Bianchi identities necessary in the equations of motions, which means that these equations of motions are not independent. And essentially, the way to express this dependence of the equations of motion, these differential identities that the equations of motion satisfies, is essentially that this quantity now is also, can be also expressed as a total differential. But now these objects which appear here, C of xi, is a constraint. What does it mean? It means that it's a linear combinations of all the equations of motion. And it means that these objects, vanishes on shell when the equations of motions are implied. Okay, so why is it important? Because now it means that if you take the difference of this identity with this identity here, you get this Noether second theorem that says that the Noether charge minus a set of constraints is completely it vanishes even when you don't impose the equations of motions. And what it means is that the Noether charges associated, let's say, with the local symmetry are supported. So suppose now I'm looking at a region sigma with boundary S, and I want to understand what is the energy of that region. And the energy is going to be associated with a Noether charge for that regions. I'm applying a vector field inside the regions. And Noether theorem tells us that the energy or the diffeomorphism charge is entirely supported on its boundary. And the way it works is that the Noether charge now becomes the integral of the constraints and some codimension to objects here, which is called the charge aspect. So it means that local symmetries are not supported by slices. They're supported by corner charges. And it says some things pretty radical. It means that the energy in your room, is just completely encoded into the value of certain combinations of field in the boundary of that room. And that's true for any subsystems or you can define there. And what it means, it's that we have a gravitational Gauss law that the energy of a subsystem is entirely encoded into an observable that lives at its corner. And this is irrespective of the matter content. It's a very generic feature. And more generally, what it means is that you should not focus on the interior energy. There's a collection of charges that capture the symmetry of what's happening in your subsystem, and they form an algebra. And this symmetry algebra is what we call the Coronal Symmetry algebra. Okay, so let me just finish with the Noether theorem, explaining you what it means for gravity. So as I was saying, in gravity, the symmetry charges, and I'm repeating the same thing, are really supported on codimension to corners. If you want, the energy of a region is not supported by any bulk data, but really by the corner data. And this is the essence of holography. So for Einstein-Hilbert gravity, we have that given any matter, the constraint is really the difference between the Einstein tensor and T. And the corner charge is this very simple universal object here given by the Komor potential, which in fact depends on just local boundary metric component. So one important thing is that if you want to understand the energy of a system, all you have to do is be able to measure the the geometry of that system around its boundary, and that gives you exactly all the information about the total energy, combining gravitational and matter energy inside. Now, the other thing which is important is that this is a symmetry charges, and it means that they satisfy the quantum algebra, semi-classical algebra, quantum algebra, which represents this boundary group. And what this quantum algebra gives us is that it gives us a representation of what are the non-commutativity of the metric components near this boundary. And if you do that for every subsystem, it really means that you have access through this symmetry to what is really the quantum commutation relation of the metric. Okay, so this is this classical Noether theorem, and now I want to explain a little bit others that affect our understanding of quantum entanglement. But maybe if there's questions I can about this classical part, I can take some.
Are there any questions at this point or comments? If not, I wanted to ask something. If you can go one slide back, Laurent, just to understand a bit better the definition of, you say that these are codimension 1-2 volume forms.
Yes. Yes. So usually a symmetry charge is given by the integral of the Noether current around your slice, right? So there's a notion that the energy, for instance, there's a notion of energy per bulk point. Okay. Here in gravity, if you want to compute the energy of a system, you find that the energy of that system is 0 per bulk point, and it's somehow completely contained into the boundary, and it gives us a picture of what really is happening in gravity. So gravity is very different from any other theory, because anytime you put any amount of energy inside a region, the gravitational, what is the gravitational field for? The gravitational field is here to compensate that amount of energy exactly in such a way that the bulk energy always vanishes, and all you're left with is some kind of differential part that is supported on the boundary. And this is really the nature of gravity. This is really what gravity does. The gravity always responds if you want, to any input of matter and energy or momenta by screening it exactly or almost exactly. And what we're looking at is the differential, what's left over. And appreciating that and understanding that means that you're appreciating how gravity is different from any other theory, where in other theory, energy is determined by per bulk points.
Lee has a question, I think.
Yes, was this recognized at the time as being an extension of the equivalence principle? Because it seems to be an extension.
Well, I mean, to some extent, if you read Einstein's first paper, yes, there's a very interesting, and I cannot go there, I wrote a paper, but there's a very interesting correspondence between Einstein and Klein where they discuss that. They dig deeper into the nature conservation law, and now Einstein was really aware of that. In fact, he was the first one to really formulate, the consequences of Noether theorem in his own way. And this balancing, this exact screening of gravity being the, something that completely screens any other form of energy. And we're going to see that this screening is the essence of what's different in the nature of entanglement. But, okay.
So is there any indication here for the entangling sphere that you write there, or this is something we're going to see later?
Is there a...
You're saying that S, so the two-dimensional sphere that is going to be the common boundary between two regions, you're saying it's an entangling sphere.
Yes, we're going to see in what way it really capture, what's different about entanglement in gravity from quantum field theory, or yes. Maybe I can move on to that and postpone maybe the second set of questions to that element, might clarify.
Yes.
So, okay. So once I've established that, that local symmetries are supported onto coronals. Okay, that was the message of Noether and Einstein, and it was understood 90 years ago and then kind of forgotten in some way and rediscovered many times. And this is, of course, the source of holography. If energy, is living on the boundary, then of course there's in some way, and this is what we're going to see. There's in some sense, this is the reason why quantum information is going to be delocalized. So at the quantum level, what does that mean? It means that if you want to study what's happening in a region, anything that you can put in that region is going to get, in fact, represented in terms of this coronal symmetry algebra, and it's going to form a vector in a representation state of this coronal symmetry algebra. And so therefore, if you want to understand what is the physics inside your box, for any box, you need to understand the nature of representations and how, let's say, certain matters or excitations affect these. And what it means is that the Hilbert space attached to that region, it organizes itself in the collections, if you want, of super selection sector, which are the irreducible representation of this coronal symmetry algebra. And once you understand that, and you understand what is the connection between the representation and the geometry, you have the fact that geometry is encoded algebraically. So the first step is really to understand, identify this coronal symmetry algebra, its representation, but also what it means for entanglement. So now let's go back to something which is maybe more KISS related, which is the notion of subregion entanglement. And there's really three different levels of subregion entanglement, depending on non-relativistic quantum theory, relativistic quantum theory, or gravity. So, I think the KISS community is more based on quantum information. So the quantum information notion of entanglement is really associated to the first level. What's happening in non-relativistic quantum theory, like condensed matter system, quantum informational system. And there, we have a notion of locality in quantum information system, and locality translates itself into property about the Hilbert space. Now, a Hilbert space of a theory contains two structures. One is a linear structure, and the linear structure, is about how does this Hilbert space decompose when I chop my basic systems into subsystems. And in non-relativistic quantum theory, we have the Hilbert space decomposes if I take two regions, sigma and sigma bar, which are complementary to each other. The Hilbert space decomposes into a tensor product. That's the first aspect. Now, a second hypothesis, which is always put in quantum information as an axiom for Hilbert spaces and tensor decomposition, but it's not true in general, is the fact that what happens in a non-relativistic quantum theory is that these two Hilbert space factor, Hilbert space also, has a metric or sesquilinear form, and it means that you can take, scalar products between them. And in non-relativistic quantum theory, you have that the different Hilbert factors are orthogonal to each other. Okay, so non-relativistic quantum theory is a theory that has a local decomposition where every, in terms of tensor product, where every of the Hilbert factors are orthogonal. Now, if you go to relativistic quantum theory, and there's a distinction between massive and massless. So in massive relativistic quantum theory, massive means essentially that you can prove that there's a unique vacuum, okay? And it means two things. It means that, in non-relativistic quantum theory, you still have the fact that, if you have different regions which are complementary to each other, the Hilbert space still decomposes into a tensor product. There's a notion of locality, which is called microcausality. You have a decomposition of the Hilbert space into local tensor product associated with the locality of the field. And it's built in our understanding of quantum theory. But now the different factors here in a relativistic quantum theory are no longer orthogonal, okay? So no matter how far you are apart from the two regions, there will be always an exponentially small non-zero scalar product between these two vectors, even if they're localized far apart. And the fact that it's non-zero is the fundamental property of entanglement of the vacuum. And this is one of the first source of entanglement of subregions that people have talked a lot about. So one way,
Laurent, sigma is oh, okay, sure. Your answer here is your three-dimensional surface, right?
Yes. Sigma is in the Hilbert space. Sigma is a 3D, and you can look at its time development. So you can think of H sigma as attached to a local diamond.
So what is H sigma in a relativistic field theory exactly? How is it defined?
You just act with all the local operators, supported at sigma on the vacuum state. Okay, and so this tensor decomposition means that
microcausality. The Slider theorem, whatever. It's okay. So that's what I see.
Yeah. So it means that this operator microcausality means essentially this is kind of microcausality, right? It means that the operator acting here commutes with the operator there. Okay, so you can independently create states on both regions, but this non-vanishing of this scalar product is the Rich-Leader theorem that says that even if this operator there is affected in terms of the scalar product by space-like region.
And can you actually write the Fock space as a tensor product?
Yeah, you can. I think the mistake that people use usually is that they assume that in quantum information, there is an assumption that a tensor product factorization necessarily means that the tensor factor have to be orthogonal. But of course, here it's a type 3 factor, so there's all sorts of technical. But yeah, this is really the difference. You can have a finite dimensional model for what is relativistic quantum theory. All you have to do is take a scalar product which is not compatible or with the tensor decomposition. This is very, very elementary, but it really focuses where the entanglement comes from. And maybe before I answer the next question, it means, this property here, of course, you can work out more, and it leads to the entanglement, which is measured through the Unruh effect. So let's say the Unruh effect is the fact that, as Carlo was saying, this tensor product is due to the fact that there's a locality of operators that commute on different regions, but somehow the support of the Hilbert space is common to all, and the support is this unique vacuum states. So this non-orthogonality of the tensor subfactor can be viewed also by taking a trace of one of the subfactor, the complementary region, and looking at what is the reduced density matrix for these objects. And the general theorem of Unruh is the fact that this reduced density matrix is given by the exponential of the boost Hamiltonian, which is essentially the Hamiltonian that preserved the causal diamond. That's a very robust and generic
Laurent,
yes.
One question: what is the role of having them space-like separated sigma and sigma tilde? It's crucial here, right? To read.
Yeah, it's crucial for this tensor product decomposition. Otherwise, if they are not space-like separated, they're kind of subset to each other. Yes.
All right.
But is there H sigma is well defined here?
Yes, H sigma is well defined. Yeah. But of course, it's not orthogonal. So I think you have to distinguish the linear structure from the matrix structures. Like when you define a manifold, there's the notion of topology and there's the notion of the metric. Okay.
I guess the question is, aren't there more states than those that you obtain? I mean, suppose you split Minkowski, I'm just getting to detail, right? Suppose I do Minkowski and I split in two like we do in Rindler, right? It's mathematically speaking, I can define the Hilbert space on the right, the Hilbert space on the left. Is that all? Or isn't there more states than those?
No. Not in quantum theory, but in gravity, yes. That's going to be the point. That's going to be the point. There's no more state because of the so-called LSZ decoupling theorem that says that in massive relativistic theory, the vacuum is unique. So all the entanglement really comes from the vacuum. There's no extra source of entanglement. So let me go to gravity, because this is where, so first you have to understand, so the first difference is going from quantum information, quantum matter to relativistic theory, you have to appreciate this Rich-Leader property there. Now, but I want to go to quantum gravity. What is so special about quantum gravity that follows from the Noether theorem? And you have, I mean everybody working quantum gravity, we have to appreciate that. And it's the following. It's the fact that now what Carlo was talking about is not happening. So now this property that you can decompose the Hilbert space into tensor subfactors like that is no longer valid in gravity. So if we have a slice that we decompose into sigma and its complement with interface S, in massless theories and gauge theories in general, the total Hilbert space does not decompose into the tensor product. In fact, if you look at the sets of local operators in sigma, and you know, local states in sigma, and you tensor it with local states in sigma bar, and you take their tensor product, you're missing some states. So this object is strictly included into the full Hilbert space. And the reason is that this local proves that in this series, you have an infinite number of vacua. There's the infinite degeneracy of the vacua. And this infinite degeneracy cannot be probed by local charge. So what's happening and why you know, what's the fix? So the fact that we're missing some states here is very simple. Let me take a gauge theory example. It means that suppose that I have a big slice, you know, which is the union of two sub-slices there. And then on this big slice, I'm going to have a physical observable, a gauge invariant observable, or the physical observable, and states are excited, you know, by action with them. But these physical observable are necessarily, you know, have some element of non-locality. And it means that, for instance, this with some loops, you know, create a states in the big Hilbert space. But if I cut and I try to separate into two subsystems, suddenly I'm going to cut this with some loops, and these subsystems here now are no longer, you know, obtained by gauge invariant observable because of the appearance of boundary charges. And if you want to restrict, you know, to a strict definition of tensor product, then you're missing these observables. So that's the essence of the observables you're missing. You're missing the non-locality of charges. So the way out is really to understand that you need to append or extend the region Hilbert space by a corner Hilbert space. And this corner Hilbert space, the way to characterize it is that it has to carry a representation of this symmetry group that we revealed through Noether, this corner symmetry group.
A short question. Can you say something about what of this is? It's the same in Yang-Mills theory and in gravity, and what's different here?
Yeah, I'm going to say that later when I talk about screening. So if you look in 2 slides, yes, there's a fundamental difference. Yes. Yeah, not only in the nature of GS, but in the nature of screening. So the first step is okay, the extension of the symmetry group. You need to add, if you want, the sets of boundary charges. And another way to understand why you need to add these boundary charges is that these boundary charges, they represent somehow the missing regions, and the missing regions has an influence on your system. And you can capture these boundary charges. And now, you know, once you understand that this boundary charges Hilbert space, this corner Hilbert space carries a representation of the symmetry group, you can define a generalization of the tensor product, which is called a fusion product, which is the fact that you take the tensor product of this extended Hilbert space, and then you have to ensure that the charges across the boundaries matches, so that you take a singlet under GS. And what this creates is that it creates a deeper level of entanglement, much deeper than just the entanglement of the vacua. This is a level of entanglement of the observable. Okay, and it means that if you really want to understand the nature of entanglement in gravitational theory or in gauge theory, you first need to understand really what is this symmetry group. Do you have the complete sets, and understand its representation theory and how to construct these singlet states. And this symmetry group and its representation is an absolutely necessary ingredient to construct quantum space-time, no matter what is going to be your theory of quantum gravity. So now let me go a little bit into what this means and how, you know, in terms of, let's say, information paradox. So is best decomposed into tensor products. This hypothesis is not valid. Instead, it decomposed into a set of fusion product where you need to have a matching of charges across the common boundary. And this is due to the presence of infinitely many vacua. So now, the hypothesis that total Hilbert space decomposing tensor product is made repeatedly in the recent literature. And you can often see that in effective field theory, the state of a system in the standard theory of quantum gravity can be specified independently on a bounded region and onto its complements. And this assumption, and I want to state it very clearly, is fundamentally wrong or incorrect. Okay. Now this is a very appealing assumption, which is incorrect, but very appealing. And this is essentially this assumption, which is the source of many information paradox. So for instance, if you look at the original Hawking paradox, the paradox that comes from the monogamy of entanglement that led to the first Bohr proposal, if you look at the firewall paradox, or even the existence of a page curve, all these notions of paradox, they all assume in their hypothesis a split property of the Hilbert space. By split property, I mean the fact that it decomposes into a tensor product, and this split property is wrong. So in some sense, we are in a logical conundrum because I'm saying all this paradox stems from a wrong hypothesis. If I release this wrong hypothesis, I don't really have this paradox. Now, for some people, that doesn't mean I've resolved the paradox, but anyway, if you're a logician, you understand what I'm talking about. So now what the Noether theorem implies is the fact that any information localized into a region sigma can be measured at a quantum level by operator. And we're going to construct again charges which are defined purely on the boundary, or if you want, charges that are defined outside of the region of sigma. And it means that there's a fundamental energy delocalization. There's a fundamental delocalization of information in quantum gravity.
Wait. Is that true? Yes. I mean, are you saying that on a given, in the bulk, you can measure anything inside by measuring something on the boundary?
Well, by anything, let's get, yeah, what I'm saying is, let me make it precise. I'm saying that microcausality, the split property is tied up with the macro locality. So physical observable on space-like different regions in gravity do not commute.
Right, yes. But you said something much stronger a moment ago. So you said that anything in the bulk can be measured.
I didn't say that. Well, yeah, okay, maybe, okay, some amount of information, whether it's any or
okay.
But I mean that if you put anything inside, it will register on the outside. There will be an effect on the outside, and this is where there's a difference between gauge theory and gravity. So let me try to exemplify.
Sorry to interrupt, Laurent. I think this is important because people I think are confused whether you're saying. I don't think you're saying this is. So this is not the same as holography, right? So if you have vacuum degrees of freedom, are they encoded in these corners? If you just have
the corner charge in some sense labels the many different vacua, right? And then what I'm saying, this is what I want to show now, is that if you put any amount of matter into a region, it will react to that vacua in such a way that that has a response onto the charge. So let me try to make that.
Yes, maybe we should let Laurent continue, cover some.
Yeah, and then maybe I can stop and I can forget about the quantum gravity consequence for that because I'm taking too much time. But let's say, so, the basis of this argument is as follows. So, if you have, let's say, you want to have a localized region, and let's say you want to put some amount of matter, you want to create a localized matter excitation. So you want to put an operator, at a given point there. Okay. Localized. Now, as we have seen, remember that the Noether theorem says that, it's not possible in gravity to have a localized information which is not screened by the corresponding gravitational field configuration. Okay, so it means that any operator which is purely localized and undressed like that violates the constraints. Okay, so if you want to have an operator which is kind of quasi-localized, corresponds to insertions of matter there, you need to kind of gravitationally dress that operator in such a way that now it's satisfying this Noether, second theorem. And it means that, okay, one way to do that is to just gravitationally dress this operator, in a proper manner that makes it gauge invariant. So now you can do that for gauge and gravity. The thing is that in gauge theory, the charges, that you're screening through that effect could be positive or negative. And therefore, it's possible to have a kind of a screening which is a quasi-local that you can contain into a small regions of space. Now, the difference in gravity is that one of the charges of the gravitational symmetry is the energy. And there's a notion of positivity of energy, which is tied up with the notion of causality, the fact that time flows in one direction. And because the energy is positive, there's no place in gravity for a screening mechanism. So you cannot just put negative energy matter to localize your energy excitation. And what that means is that whatever screening you're going to put in gravity, it has to extend to infinity. Any gravitational dressing or physical observable insertions of matter has to have a tail, if you want, that goes to infinity. And this is due to the positivity of energy. It's due to the fact that gravity is the only truly, long-range force in the universe. Why gravity survives for the dynamics of the universe, and we don't care about electromagnetism, is because every other force has been screened, but gravity cannot be screened because of the addition of mass. And so what it means is that the picture you need to have is that you need maybe, you can select the subregions there where the screening is supported, but these regions, where the gravitational screening that neutralizes Noether theorem extend to infinity. And since the energy, as we have shown, is localized on the boundary of there, you're going to have that, the reason you need that screening is essentially related to the Noether theorem. We say that the energy is localized on the boundary, and any excitation you put somewhere is going to carry some energy, and therefore it's not going to commute with the energy operator. So as an example, let's say, the energy operator, the total energy of, let's say, round sphere here in coordinate RT is essentially going to be some local component of the TT, the second, radial derivative of the TT component of the metric integrated over the sphere. And of course, there's this factor 8 pi g. So of course, all this reasoning really goes away when you put g Newton to 0. And this energy, does not commute with the insertions of a physical operator, because a physical operator carries energy. Now, in general, it's true not only for the energy, but it's true for any generator of this corner symmetry group, that the charge generators localized outside the region still capture information about operator insertions inside this region. And going back to this fusion products, what this operation shows is that if you want to put a local operation and dress it gravitationally, then what you're going to show is that physical operators, which are associated with space-like separated regions, in fact, do not commute with each other. So of course, physical operators associated, let's say, with an external of a region has information about what happens inside that region. And a central element of this, if you want, delocalization of information is the symmetry charges, okay? So I hope this answers some of the questions. And what we conclude from that is that we can understand state of geometry inside a region as state of representation of this corner symmetry group. And the goal, which I don't have time to explain here, is to ensure that this boundary or corner symmetry charge capture all the necessary geometrical information about what is the nature of geometry around S.
But do you take questions, or?
Yes, I think it's a good time to take questions.
Is it a goal, or is what I do understand what you're saying, but what I don't understand is whether two different bulk operators can have the same boundary effect. In other words,
yeah, and that's what we're studying. So first is to understand what is the nature of this symmetry group, make sure we have the full symmetry group. So this is under construction, understand its representation, and look at the degeneracy. And the story of the symmetry group is that we started from smaller symmetry group, and by building the full symmetry group of gravity, the bigger it is, the more information it contains about the boundary. And then the only place where we really have full control yet is when you put that boundary at infinity. That's the context of celestial orography. But what's clear is that the assumptions that an operator. So what's clear is that there are operators which are outside the horizon of a black hole that knows what's happening inside the horizon of a black hole. because of the elliptic nature of the constraints and the screening mechanism. So the assumptions that these Hilbert spaces are commuting with each other is not valid. Now,
right, but it seems to me the question, I mean, if I have a balance, every time I put something on one side, the other side knows about it. But there are many possible ways of putting something on one side which affect the other side the same way.
Yeah.
So it doesn't mean that one side knows about the other one.
Yeah, and there's many different charges, and these charges are directional. So maybe I can go more into the detail of these charges. So
okay, Lee wants to.
This is, now we are matching infinity with infinity. So the counting is, is there a leftover, and we have to be very careful into the statements we made there.
Excuse me, Lee, but how do we try to open the discussion a bit after Lee's question?
Yeah, I think we can. I can stop there. The rest of the talk was more quantum gravity.
We can take some questions and you can continue a bit with your slides. Lee, you go first, and then if anybody else has a question.
Very, very quick. Laurent, if you divide the system into subsystems along different systems of boundaries, you get something like an algebra that connects the different ways of decomposing, something like a hiding algebra.
Well, what you get is, as I was saying, you get an algebra associated with each subsystems. This algebra, and then of course the concatenations of these subsystems together is more that you're looking at the nature of intertwiners of these algebras.
Right.
So the dynamical process of somehow dynamics enters through a kind of a fusion process, if you want. But the first step is really to reformulate all the classical geometry in terms of instead of talking about metric, now I want to talk about the charges, and instead of and then I want to understand what their commutation relation, etc. So
very good.
Maybe one point of contact I can make with KISS is that it's this notion of extension of the Hilbert space or edge mode. So I'm saying, if you have a region, you have an algebra that acts in the boundary of the region, and you have a corresponding Hilbert space representation. And this a generic Hilbert space representation is what we call the edge mode. It's just the space of L2 functions is the regular representation of that group. Okay, and this regular representation is really the mathematical proper definition of what you would call a quantum reference frame. And the idea is that when you have a subsystem, the subsystem is placed into an environment, and you can ask, what is the effect of that environment on that subsystem? What is the essence of what this environment means for that subsystems? Mm-hmm. And the theory of quantum reference frame is essentially that you can think about the external system as providing a reference frame for the subsystems, and this Hilbert space here is a space of representation for this reference frame. So this connects very beautifully with the work of Giacomini, Bruckner, but also the group of Eun, Sylvain Carosa, Thomas Gelley, and also Carlo has some work about somehow this. A boundary Hilbert space as being the glue you need to connect back the states together. Marco,
a question about this, but we'll come back.
Laurent, would you like to continue a bit on your slides and then take questions?
Yeah, well, Marco had a question before, and we already.
All right, Marco.
Can you hear me?
Yes.
Yes. Okay. So as far as I understand this whole story so far, it sort of assumes from the beginning that there are some charges, some conserved quantities, locally conserved quantities in the theory. Because I mean, in general, there are no global symmetries in space-time. So this whole formalism, I mean, am I correct to understand that this whole formalism basically relies on the assumption that like energy is conserved or something like that. I mean, there is a time translation symmetry of space-time or something like that.
No. So maybe I was not clear about that. So this was, so it does not assume that at all. So what I was saying with respect to the Noether theorem is that what you're talking about is the first Noether theorem. You know, there's a notion of symmetry, which is global symmetry, which have charges supported on codimension 1 surfaces, and they require these charges to be conserved in time. Now, the Hilbert puzzle and the Noether resolution is that when you have local symmetries, there is no, the charges of symmetry are not supported on codimension 1 surfaces, they are supported on codimension 2 surfaces. And this energy conservation in some sense is kind of trivial because we're just saying it's a balance equation, it's 0. Now, what I want to talk a little bit about is so, and this, what we have is that this symmetry charge, they form a canonical representation of a symmetry group, even if there's no conservation laws for them. I mean, one of the study that is part of understanding the dynamics of this theory is what happens when you now move the entangling sphere and how much these charges transform under the motion of this entangling sphere, right? And understanding the motion of this entangling sphere is the same thing as encoding radiation going through this motion. So this is really where the frontier of the study is, right? So now the idea is to understand algebraically the notion of radiation as the continuity equations for these charges. Does that answer? So there are charges for local symmetry. Charges are corner charges. And the non-conservation, the conservation or non-conservations of them is associated with a process of dissipation, if you want. And understanding how these charges evolve in time is really understanding the nature of quantum radiation.
Okay, because I was a bit confused. What we did previously was to write down the expression for the first Noether theorem and then for the second Noether theorem, and then you subtracted the two, which assumes that, you know, there is a global group of global symmetries and then a group of local symmetries, and then you use them both in a sense.
Well, what Noether proved is that if you have a group of local symmetry, of course you can take any subgroup you know, you can take any subgroup of global symmetries inside of it. And then Noether says that if you take this group of global symmetry and let's say you fix the action of the symmetry group on the boundary, then your charges vanish, it's 0. So this goes back and answers Hilbert puzzle is that there's no, I mean, energy, if you want, is conserved, but it's trivially conserved because it just vanish, okay? Of course. And then what I was, going deeper is that this local symmetry, they kind of localize on the boundary of the system, and this delocalization of the energy is very important for the nature of entanglement. Okay, so yeah, it's very, this is why you really have to distinguish this notion of global symmetry from local symmetry, and appreciate that local symmetry do have symmetry charges, which are codimension 2.
Yeah, okay. Thank you.
Thank you. Deepak?
Yeah, hi, Laurent. So I have 2 questions. The first is that can any 2-dimensional space-like surface be an entangling surface? So for instance, if you're talking about like a black hole, then one would think that there are certain special surfaces, like for instance a trapping horizon or a marginally trapped surface, right? So is there any way to distinguish surfaces?
So yeah. So the first answer is yes. Any surface can be an entangling surface. It's kind of you as the experiment. What is your system and where is it? Now, about the fact that there's maybe special surfaces which are physically defined, this will show up when you look at the state of representations. For instance, the entangling surface of horizon, the bifurcation surface of horizon has very special property in terms of the representation theory of that corner symmetry group. For instance, it's a surface where most of the Casimirs vanish, so it has extra regularity. But in some sense now, when I look at a surface, I can characterize its property in terms of what are the Casimirs, for instance. But any surface is interesting. Yes.
No, but so the point is that this corner symmetry algebra allows you to distinguish certain special surfaces. There is some criteria that you can use to.
Yeah, you can use extra criteria to understand, what are the special representation theory attached to it. So for instance, it's well understood that at infinity, where you have surfaces that cuts sky plus, right? And then there's two special surfaces, which is I naught, and then there's I plus, which is the future of infinity. And you can show that the entire process of radiation is that you take any charge at I naught, and then you evolve it along sky plus, and essentially I plus is the point where all the Casimirs vanish there. Okay, so that's the definition of time like infinity. Okay, it's a place where all the Casimirs or all the representation trivializes there. I know it is more complicated to describe in that way. Okay.
Thanks.
Thank you.
Maybe we can
yes.
postpone some questions. I mean, I don't know how long you.
Yes. Continue, please, Laurent. I'll come back to the questions.
Yeah. So okay, I wanted to talk about this, edge mode states, and then there's a semi-classical representation for it, this edge mode states, which is in terms of the embedding field. If you want, this edge mode states is a state of representation for a field that lives purely on the surface, which is like a fluid field, is like the Euler frame of the boundary, which essentially says where is that boundary placed in space-time, so it's kind of a where it's a representation of a map from a portion of RD to your manifold, and because of that, there's a notion of left action, which are gauge, and right action, which are symmetry, and that allows to distinguish what is gauge and what is symmetry. Now, to understand deeper what's happening in quantum gravity, we I haven't said anything about what is this group for gravity. You need to understand a bit more what is the space of representation, because this is this representation that really measures the entanglement across a region. And then what do we conclude from it? That is, how much of understanding the symmetry determines the dynamic of gravity? Okay, this was the questions of Carlo, for instance. Or can we say something about area quantizations of nature of the degrees of freedom? So I'm going just to skim through it very fast. As I say, so gravitational subsystems, obtained by considering a slice sigma, decomposition into subregions. To subregions, we associate what we call the extended corner symmetry group. And, to identify this corner symmetry group, you just look at the space of local symmetry transformations that have a non-zero vanishing charges. Okay, that's the definition. Everything which has a vanishing charge is pure gauge, you're quotient by it. Everything which has a non-zero Noether charge is pure symmetry in sense of global symmetry there. And we can decompose this. So what's happening is that you have a sphere there, you have a group, part of the group of symmetry is diffeomorphism. And of course, you're going to look at all the symmetry group, with respect to that sphere. And what you find is that there's a subgroup which is not vanishing, and the subgroup contains the diffeomorphism of the sphere. So any kind of relabeling or deformation of the complex structure of that sphere is allowed. It also contains the possibility to translate along normals that sphere. This corresponds to vector field that do not vanish in that sphere. And a very important element of the corner is that it also contains also a notion of boost transformation. That is a notion of normal rotation. If you want, when you have a sphere, you can make boost around that sphere. And this boost parameter could be different at different points of the sphere. Okay, so this subgroup here is called the corner symmetry group. It's the subgroup that doesn't move the sphere, and because it doesn't move the sphere, it has a naive canonical representation. And this other group is called the group of supertranslation, and this group of supertranslation is the group that somehow knows about the dynamics of the theory. Okay. What we're saying is that this particular group is canonically represented on the gravity phase space. Now, there's two important theorems about this group, is that all physical observable have to transform covariantly under it. I was saying, if you put a physical observable, it does not commute with that group. It's just, it has to transform under it because of the positivity of energy. Now, another thing is that this group is universal. It follows from a work by Wald, but also Speranza, that says that if you take any theory of metric gravity, and you can take any arbitrary derivative for this Lagrangian, you're always going to find the same symmetry group. So it's absolutely robust under any deformation you can have, or any non-local deformation you can have of your gravity theory, higher derivative deformation if you want. What's going to change is the canonical representation of the Noether charge, but the group of symmetry is still going to be the same. And it's also, what we can show is that if you take that group of symmetry and you expand that sphere and you push it to infinity, this symmetry group simply reduces to the old well-known BMS symmetry group or its extensions. Essentially, in BMS, you have a part of the subgroup, which is the diffeomorphism on the sphere. The normal boost becomes some kind of Weil deformation, and the super translations reduces to super translation along the boundary. So symmetry group of asymptotic infinity can be viewed as subgroup of this Coronal symmetry group. So it's kind of a very, the message there is it's very robust, very universal. It's the same group no matter how much derivative corrections you have to reaction, and it's the same group, no matter how big or small you take the sphere. So there's a group for small sphere, a group for big spheres. They're all related to each other. What changes is the nature of the representation of this group. And I don't have time to explain that, but the idea is that, if I look at a metric component near the surface of the sphere, where it's a sigma coordinate along the sphere and xi are normal coordinates, then the metric has three components. It contains a normal metric, a tangential metric, and some kind of a mixed indices that mix the normal and tangential components. And what you can show, so one of the questions of quantum gravity is, after you impose the constraints, how do these objects commute with each other? Of course, before you impose the constraints, the metric on a slice commute with itself, but it's not true after you impose the constraints. And the idea is to understand any of these components of the metric in terms of corner charges. For instance, the normal metric is essentially the charge for this SL2R symmetry, and that determines exactly how this metric component do not commute with each other. And it establishes the nature of this, if you want, entanglement of operators. Our operators located here and here do not commute through the non-commutation of the metric. And if you're interested into discretization, it means that if you want to discretize your metric in a node, that node needs to carry a representation or a truncation of that representation of that corner symmetry. So I'm not going to, this is another talk to show you how these objects, the normal metric, the normal laps are encoded into this symmetry group. The tangential metric is interesting. It's more subtle. It only reveals itself as a charge of symmetry if you introduce the immediate Z parameter, which is well known to loop gravity people. Otherwise, it's not accessible through the symmetry algebra. Maybe let me skip that. One recent development is the fact that, as I was saying, there's in this corner symmetry group, there's what I call the corner symmetry, which is canonically represented, and there's the super translation, the one that moved the surface around. And if I move the surface around and there is radiation, then I cannot expect the charge to be conserved. And these non-conservations of charges is really encoded into a notion of a symplectic flux, which is a one form on your phase space, or it's an operator if you want labeled by a vector there. And this symplectic flux control the way the symmetry charge changes when you move your surface around. And what's important is that the way the charge changes is exactly related to the way the symplectic potential changes. So if you think the symplectic potential measures the number of degrees of freedom of your theory, and if I have a surface inside the bigger space, move it in time, then you have the possibility to come in or gets out, depending on the nature of that surface. And that means that I'm losing or gaining degrees of freedom. So there's a notion of symplectic flux. And this is what this operator encodes. So we understand the nature of this operator. And this operator also encodes the way the charge is transformed. So there's a direct connection between the loss of information and the loss of energy. Okay, that's the essence of this more elaborate Noether theorems there. And what we've been able to show is that even in a case, so if you think about the complexity of quantizing gravity, is that you want to be able to quantize a system, or let's say subsystem, which is open. And that seems like a contradiction in terms, right? Because we think that usually open systems are thermodynamical, they are not quantizable. But it turns out that in gravity, once you introduce this embedding field or this Edge-mode field, you can show that even if the system is open, that is, even if there's a non-unitarity in the system, it is possible to have a representation of a canonical representation of the charge. That is, it's still possible to show that the Noether charge is a canonical generator for your symmetry, even in the case of the open system. So this is a new result there's two groups that worked on that. And I think it's a very exciting result because it opens the possibility to give an Hamiltonian treatment of gravitational open subsystems. And this is not possible if the system is not gravitational. If you have a non-gravitational open system, there's no Hamiltonian treatment of it. But for gravity, it turns out that there is. And I think we're going to learn more from that. One maybe last thing for people who are from loop gravity. So I was saying, this corner symmetry tells you that you have you want to understand somehow the representation theory of your corner symmetry group. And the way to think about that is to think about that sphere as supporting a corner fluid, okay, which is representing of your quantum gravity degrees of freedom. And there's a direct analogy between gravity in the bulk and codimension one fluid dynamics on the boundary, where the area density plays the role of the fluid density. And it means that if you can prove somehow, if you can prove that this fluid is made of molecules, it essentially means that the density of the fluid or the area formed is a sum of delta functions, for instance, then the fluid molecularizations corresponds to the area quantization. And then from this fluid picture, you can really construct the Casimirs of the theory. One important Casimir is that you can show that the total area is a Casimir. So of course, there's going to be a link between the number of degrees of freedom in your system and the representation you're picking. And one of the Casimir is the area, but there's others there. And this quantization of area can be proven at the molecularization, if you want, of the corner fluid, can be proven in the continuum theory. And it necessitates the presence of this Mirzi parameter. So let's connect with a famous result in loop gravity. Okay, as I mentioned, okay, there's a connection with celestial holography. If you take large sphere, you're getting the same representations that degenerates at infinity. If you take a large sphere, it's like taking a semi-classical limit, so any area gap will be lost if you just work from the point of view of infinity. But a lot of the same structure survives. And as a conclusion, so what I wanted to convey is that there is a profound consequence of Noether theorem for gravitational theories that leads to a new picture of subregion entanglement. The Hilbert space associated with subregions needs to be dressed by regular representations of the corner symmetry group. This entanglement encodes, and this dressing encodes the non-commutativity of physical observable, even when they are space-like separated. So you cannot assume in a gravity theory that space-like separated regions commute because they have to share this corner charge at their common boundaries. And it also implies the presence of non-commutative algebra associated with subregions, and these non-commutative algebras are a way to encode the quantization of geometry. In some cases, you can get from there a discretization of space from the study of the representation of this algebra, which are non-commutative, infinite-dimensional algebra. And I will stop there, and thank you for your attention. Sorry for the talk being too long.
Thank you very much, Laurent, for the fascinating talk. We go directly to questions. There are several hands. I think first was Christy Stoika.
Well, hello. It was a very nice talk. Thank you very much. About these two problems that are so important for quantum gravity, I would say the entropy of a black hole and the black hole information paradox. I think so. It is the reason I was a bit I don't know, disappointed by so many approaches. It was that they both were derived from quantum field theory on curved spacetime, mainly semi-classical. So you have general relativity, you have quantum field theory, and you combine them in a very conservative way, and you derive both the black hole entropy and also the information paradox. And the reason I was so disappointed by so many approaches, or should I say skeptical, was that most of them try to add some degrees of freedom that then they want to count to recover this entropy or this information lost. And it seems to me that the approach you presented in this talk is very conservative, in the sense that you start with general relativity and quantum field theory, basically Noether's theorem, and try to derive from them whatever information might be needed to solve this and other problems. And for this reason, I think I'm, for the first time in a long time, optimistic, unless I'm wrong and I misunderstood your approach. So thank you very much. This was more of a comment, but if I was wrong, please correct me.
No, thank you for your comment. This is exactly, I had the same misgivings, if you want, and this is exactly what I'm trying to do. Understanding there's something very profound about the screening that Noether theorem implies, and you can go a long way without knowing exactly what is the ultimate theory there. And the goal is not to postulate these degrees of freedom, but see if we can see them emerge from that analysis. Very good.
Yes, thank you.
Thank you. Wolfgang?
Hello, hi, thanks for the nice talk. I have basically one question. So you mentioned several times during your talk holography, and from the stage of the development right now, I just don't see anything else than a very important development, namely the quantization of gravitational fields in the presence of boundaries, and the quantization of boundaries themselves. However, I don't really understand, or I don't see a clear statement about holography. So is the statement, in other words, that all there is are charges or symmetries localized at two-dimensional corners, or is there more? Are there also bulk degrees of freedom that then characterize the two polarizations of gravitational radiation, and the edge modes, and that would be more my understanding, are charges, like they characterize momenta, angular momentum carried by the radiation inside, for instance. And then perhaps also a second question, more of a technical one. You stressed at some point very nicely that area is a Casimir of your boundary symmetry algebra. But if it is a Casimir, one would suppose that it commutes with all the other generators, but that would exclude the possibility that area changes, as it does under the influence of incoming radiation and so on. So perhaps I would be happy if you could answer some of these questions. Thanks.
Yeah, okay. So concerning the first statement, it's true that holography is a very loaded word, and when you know, that's why I was trying to distinguish, I don't know, ADS-CFT holography, celestial holography, and local holography, because they have different, somehow they mean for me very different things. So the first statement you were saying, which is maybe the ultimate purpose of holography, is to show that maybe you can encode everything from the point of view of the boundary. This is more the statement of ADS-CFT holography. Here, I was trying to build from the ground up and saying that, okay, you know, the reasons behind all this holography is the gravitational Gauss's law. You know, energy is delocalized, and you have to focus on that. And now the question is, can you really understand the picture of physics in terms of exchange of energy, in terms of fusion of energy, etc. If you could, then there's a chance in which you could maybe reconstruct the dynamics in terms of its boundary charge. But I don't want to make grandiose statement. I want to have the setup there and then build up towards that that construction. The only thing that we have so I don't think the answer is done yet, and I think that's part of the program. You want to understand better what is really the nature of the symmetry algebra and how much of that it contains, how much does it contain, about the dynamics. There is some very interesting developments, recent development in celestial holography, which I view just as large sphere, where there, we were able to show, so two things. We were able to show that the notion of the symmetry algebra, so demanding invariance under the extended symmetry group, allows you to reconstruct the asymptotic Einstein equation. And that's kind of very surprising to me, in the sense that the symmetry groups are powerful enough to somehow know something about the dynamics. So now this is only the asymptotic dynamics, and there's the question whether you can go inside. And there's a new interesting development about this W infinity algebra. So I think the jury is out there. These groups are very powerful, and we are just learning how to use them. Now, concerning your second question, it's related. So when I was saying that the area is a Casimir, I distinguished, maybe I was fast, what I call the corner symmetry group, which is the symmetry group which is canonically represented from the extended corner symmetry group that contains the super translation. So, and so what you have to show is that the area is a Casimir of this subgroup, the corner symmetry group. Now, if you start to translate the sphere, and if there is radiation in the game, as you're saying, the area is going to change, and somehow this is the way the dynamics enters. The dynamics enters from the fact that there's two levels of dynamics. One is that there's some kind of dynamics which is inside the orbit of the subgroup. And this is the dynamics of the, this is the way you label the states. And then there's the dynamics of radiation. That is the fact that when you move the surface around, there's a distillation, or there's a dissipation. And the dissipation is measured not through the charges, but through the Casimirs. So what we're trying to do is invert that map, like from the dynamics of the Casimirs, how much information can we construct from the radiation? I hope that answers your question. And we have some successes at infinity, but in the bulk, it's complicated. People are studying really the nature of charges and motion of charges along null surface. So this is an area of current development.
Thank you. Lee, you want to comment before we move on? Yeah.
Well, I'll add a question before me.
Go ahead. It's not a comment. It's a new question.
Sorry, Lee, do you want to ask your question?
Yes, no, I'd be happy to. Yeah. Laurent, it's beautiful. It's a beautiful picture, but I have two simple questions. If I start off with some compact spacetime, and I divide it in different ways into subsystems, and for each subsystem there's a corner dynamics, a corner Hilbert space, a corner algebra. how much is the statement that, like topological field theory, no matter how I divide it into subsystems with different corners, is a way to reassemble everything so that there's a unique description? Is there an algebra that tells you what the result of changing the division into different subsystems is, or uniting two subsystems? That kind of question.
Yeah, totally. I mean, here, yeah. So there's several operations. There's what is the nature of one region, then what is the nature of the gluing, and now if you have free gluing, you're creating corners of corner, and then you're going to have some kind of associativity conditions.
Yes.
So you're going to enter, once you understand the representation of this group, and maybe for you this group is just SU2 if you want, but let's say I'm just going to replace your loop group by this Coronal Symmetry group, which is more fundamental, and then of course ultimately, yeah, I agree. There's going to be some higher categorical description of that space, which means that the decomposition of regions and subregions need to go up to the point, in fact, and in gravity we're far from that. In topological field theory, in fact, it's only very recently that people were able to decompose, let's say, Chern-Simons up to the point, and it's a very beautiful, interesting structure. So, but this is much farther in the future. You're going back to old ideas of Crane, of a very categorical construction. But here, I wanted to link it to very simple things we know.
But is there a most elementary corner description, and is that somehow going to be?
I would imagine, yeah. It's the ultimate corner is what is the quantum point? So what's the point?
What's the
point? What's the point?
Event.
Yeah, exactly. What's the point? What's the event? But
very good.
We're not there yet. We have to cut it down. Yes.
No, hurry up.
Well, yeah, but I want every step to. I think we have been, for me, in quantum gravity, we have hurried towards the description of the point. So I want to be solid, whatever basis that any theory of quantum gravity needs to agree on that. Like you cannot avoid, telling me the nature of your representation.
Thank you.
Next was Al.
Next was Lin Kin.
Oh, Lin Kin.
Then we'll go to Hal.
Thank you, Laurent, for the great talk. I have a question that recently there was a very surprising and strong result shown by Soviet Raju and his collaborators by preterperatively solving Wheeler-DeWitt equation at low energy for ADS background. And they shown that even at the level for wave function, so the two wave functional of gravity coincide at the asymptotic boundary of the Cauchy slice, they have to coincide everywhere in the bulk. And this is a very surprising result, and I think it is compatible with your framework. Do you see a simpler way to understand this, like intuitively, or the validity of such a strong result from your framework, or even non-preterperatively?
Yeah, no, that's a good question. Yeah, I agree. At some point, I mentioned Suvrat's work there, and I wanted to connect. So, I mean, the descriptions I had of the screening is the essence of the mechanism there. Now, I agree. It would be nice to have a deeper understanding, which is of the sharing of that screening and whether this charge representation is enough to reconstruct all information, as Suvrat claims. I think there is. There's I mean, the spirit, I think, of what Suvrat is doing is totally correct in the sense that he takes what people were doing before, saying there's a split property, and saying, no, you're just incorrect. And the non-split property is very, very strong. The best way where we really understand that is that if you take the Bondi mass, the Bondi mass is just essentially the time component, the metric near a portion of the null boundary. You can show that the correlation of the Bondi mass with any amount of radiation in the future of the point of the insertion of the Bondi mass is non-zero. There's an algebraic tail, and you can try to do an algebraic reconstruction of the radiation from the measure of the Bondi mass. That's another. So I think, yeah, developing Suvrat checking or making sure that this statement is robust. There's a puzzle about that statement, which I'm trying to understand, which is that this statement seems to contradict a very important result of Scorvino and Schoen about the tubular modifications of Einstein's equation. So, you know, you have to understand, anyway, you have to understand a little bit, more needs to be understood to really bridge the two picture. We're going in the same direction. There's a local entanglement, and I want to link that entanglement to the presence of this symmetry group. Yes.
Thank you.
Thank you. Hal?
But yeah, I recommend people to read Suvrat's results. It's very nice.
Thanks, Laurent. Nice talk. I wanted to follow up on, I guess, on Wolfgang's second question and on Lee's question. I was interested in the physical interpretation of this superselection that you were mentioning. So if I consider a Planckian region, what is the meaning of the superselection? Are we talking about just fixing the area of that region, or are we talking about more than that? And so ultimately, at some level, the analysis you did for us today was more classical and semi-classical. And so I'm really curious about what is our conclusion about what we can say about superposition of spacetimes. You're saying the boundary has some fixed properties. And so what kind of superposition can we do in these small regions?
Yes, okay. So yeah, you're right. I didn't have time to really go into the representation of this group of symmetry. So now, if I look at this boundary sphere, and I have to go back to the fluid analogy. So if I have a small regions there of that fluid, which is like a fluid parcel, what you have to appreciate that there's a very, very important symmetry. The core of that symmetry is really the diffeomorphism of the sphere, which is the relabeling of the fluid lines. Okay, and so which means that the central algebra that you want to represent is not ultra local, like in loop gravity, where you can isolate a portion of the sphere and imagine that it's well identified. What I really skimmed through is that when you look at the representation theory, a very important part of the representation theorem is that the representation of these groups are essentially, you need to go down to the Cartan subgroup if you want, and you can see that the essence of the representation theory is classified by the representation of the little group, that is the group of area preserving diffeomorphism there. The same way that when you represent Poincaré representation and you fix the mass, then what you're left with is a representation of SU2. And this suggests the fact that you have, it suggests that if you really want to understand the nature of this fluid, you have to understand the nature of quantization of area preserving diffeomorphism. And there, to understand really what is this Planckian area, there's a very interesting or intriguing correspondence that it's well known that this area preserving diffeomorphism can be deformed and represented at the quantum level in terms of matrix model, or in some sense in terms of a fuzzy sphere. So I don't know the ultimate representation there. I think for people who are in loop gravity, the one thing that you have to appreciate is that gravity is about diffeomorphism symmetry, and you need to include the operation of relabeling of the fluid lines. Okay, and if you don't have that, you're missing essentially a very important element of your geometry. For instance, you cannot reconstruct the frame field and operators that are needed to reconstruct the charges and the constraints. So this would be the emphasis.
So you, as you're saying, that you're still, it's work in progress to understand the representation theory. Are at least the Casimirs or the labels of the super selection sectors clear? Is that clear?
Yes. Yes, yes, this is clear for the Coronal Symmetry group. And it's beautiful. It's really beautiful. But I will need more time to. So this is completely clear. For the full group that includes the translation, it was not clear before because it's only very recently that we have a canonical representation of that super translation group. So we're just working on complete classifications of representation for BMS, which is a subgroup. which is not known. So all of these things are, it's like when people discover the Razor group as the group of symmetry that organize all to the symmetry. It took a few years before, to understand the nature of the representation of the Razor group, and that's what we're doing right now. So there's very elementary works to be done into understanding the nature of the representation of this loop group or higher dimensional loop groups. And it's very rich, and it connects to, the theory of quantum fluid or superfluid, interestingly. 2D superfluid.
I fully believe that the full mathematics would take quite a while to develop, but can you summarize even just what the physical content of the labels of the super selection sectors
Yes,
are?
so for instance, okay, well, very good. It's so you have a two-dimensional fluid, and think about the weather system. So if you look at the weather system, it's a chaotic system, things move around. But how do you predict the weather? The way you predict the weather is that you identify a symmetry group here, which is the group of area preserving diffeomorphism, because you can treat the sphere, the Earth as some kind of compressed, incompressible fluid at some approximation, and then the way you preserve so then you can classify the Casimirs. Why are the Casimirs important? Because the Casimirs are the variable that moves slowly, right? So in a chaotic system, there's a variable that moves very fast, and the Casimirs are just the ones that are due to dissipations and they move slowly. And what happens in a weather system is that the variables that move very slowly are the vortices, right? So how do we predict the system is that people follow and pinpoint down the size and the strengths of vortices, and you can see a vortex, even in the chaotic system, stays there for 4 or 5 days, and then it moves slowly, and then they collide and they grow, and so it's clear that this is what I was saying here, that the Casimirs are labeled, and the vortices, so first you need to construct the vorticity of the fluid, and then the corresponding Casimir is called the entropy. And this is what people that predict weather do. They forget about all the fast variables. They only focus on the slow variables, and these are the ones that drive the dynamics. So I think there's a similar, maybe interesting decomposition of gravitational dynamics that needs to be done in the same way we study the system. So, the study of these vortices and the way they fluctuate. And you can think of this vortex as being the quanta of this area preserving diffeo. Okay, so the understanding their nature is and whether they're quantized or not is very important. So what I'm saying in fluid dynamics, you can take an analogy. There's 2 levels of quantization. One is, is your fluid a continuum fluid or made of molecule? And this corresponds, is your density or area a continuous measure or discrete measure? And then once you have a discrete measure, there's a second thing, is your fluid classical or quantum? And a quantum fluid has quantization of vortex. So these are really the 2 elements of a fluid. It's the density and the vortices.
And am I right in understanding that this would provide a restriction on the kinds of superpositions, quantum superpositions we could imagine happening on the interior of that region?
Yeah, maybe. I was, yeah. That's an interesting point. I was thinking more in terms of the dynamics, how you separate slow and fast variables, and anyway. But yes, I think I'm sure that this will provide a new way to organize the observables and the correlation functions.
Thank you.
Thank you very much. Carlo had a question, but he left. Is there anybody else that would like to comment or make a question of the people that haven't said anything yet? No? Okay, so last round of comments and questions for anyone before we thank the speaker.
It's a beautiful, beautiful set of work. And I'm just stunned because meanwhile, some of us have been working on matrix models and relationship between matrix models and general relativity, both classically and quantum mechanically. And this is really going to be an exciting set of developments. It's lots of things. So thank you.
Yes. Yeah, Marco, I would like to make a comment, but go first.
This is just a very short question. Can you give us some literature, some papers where you have where we can read more details on this? Is there are there? I mean, have you written this down in some review paper on the archive or something?
I'm working. There's no review paper that submits so far. It's collections of work. So if you follow the work that I have done, and in collaboration with Daniele Pranzetti, but I'm after this talk, I'm trying to put together a summary. So hopefully soon enough, there will be a more general pointer and less technical.
Okay, thank you.
Thank you. This is fantastic.
I mean, there's an interesting original work, which is the work I've done with William Donnelly in 2016, and it is the source of all this subsequent work or reflection for me. So that's always a good. It's a very fundamental understanding of where's the difference between gauge and symmetry, and I think it informs a lot of the subsequent work.
I wanted to make a general comment. So obviously this is a lot of spectacular work that has to do with building up a quantum theory of gravity. You were trying to see what are the points of intersection with things going on in quantum information, and you pointed out quantum reference frames. So let me put out something very tentative. I have to think about it. There's a big discussion and a lot of confusion on, which is why we're asking you in the beginning about the factorization of the Hilbert space, on how to apply the notion of subsystem local operations, which is a very central notion in quantum information theory, which has to do essentially on whether you have a tensor product structure or not, and on how to apply that to quantum field theory, where everything seems to be entangled. You don't seem to get this tensor product structure, even if you go to separated surfaces, basically because of the presence of constraints. And I think there is many people in the quantum information community that are catching up on these edge modes discussions exactly for that, trying to see if that would be relevant to understand what you mean by local operations in quantum information theory.
No, I think, yeah, I agree that I think the connection is through these questions of, is it possible to create superpositions of, quantum geometry and understand that locally, and this, the tying up with the quantum reference frame. What I was trying to do is distinguish, there's two levels of confusion. In quantum field theory, there is a Hilbert space decomposition into tensor products, okay? The entanglement is really due to the non-factorizations of the scalar product. And then in gravity, there's a deeper level of entanglement. So I think the problem with quantum information is that it has to catch up on two levels, right? It has to catch up going from non-relativistic quantum field theory to relativistic one, which is allowing tensor product factorizations to be non-orthogonal. But then it also has to catch up onto the quantum gravitational one, the fact that there's some kind of local operations which are well defined in field theories. They have a kind of a representation tail, and I'm sure there's and this is what maybe people are doing in quantum reference frames. There's a deeper formalism or a deeper level of quantum information, or the way it raises a lot of new questions about what does it mean. For instance, the notion of entanglement, entropy, requires the existence of tensor product factorization. So when people just talk about entanglement, entropy, in quantum field theory, it's well defined, but in quantum gravity, it is not. So there's a lot of upgrading that needs to be done there. And in fact, the work of Raju is interesting there, because Raju is, there's people who are doing quantum information and, let's say, the island, quantum gravity and this notion of island and code subspace isolated from the asymptotic infinity. And now there's a question whether this quantum information axioms are in fact, justified in a theory of quantum gravity because of this delocalization of information. So I think there's a very interesting question about, is there an upgrade of quantum information that integrates in its axiomatic the foundations of this entanglement I'm talking about? I don't think it exists yet. And
the other question, I think, just to add on this, mainly transferring things that are being discussed, is to what degree in gravity we're taking too seriously the exact nature of the long-range effect of gravity, because if you really take seriously that it's going to be potential that goes like 1/r and cannot be screened, and that will really have a measurable effect, you are ignoring the fact that there are quantum fluctuations, and in fact you may not be able to operationally distinguish the two states.
No, I think you're not taking that seriously enough. I'm sorry to interrupt. But
yeah, no, please. That should be taken seriously. Yeah.
Absolutely.
Yeah.
I think this is part of the message there. There is something very, different about gravity, is that the charge is positive. So it has to do with the nature of time. I'm not saying I understand that, but yeah. So if you were to not take seriously that, it means not taking seriously the fact that time is kind of a different entity in some way. So it's a whole package. So I think, there's something very, there's something very different about gravity, which is one, the screening, and the fact that the screening cannot be screened itself. You cannot anti-screen the screening. And that has to do with the nature of time and causality. And this is really what the long-range nature is really meaning at the quantum level. So another element there is part of the Noether theorem. If you look at her abstract, she said the converse is true. So in some sense, she is saying something that if you have that, then you have gravity. That is, if you, she's proposing the fact that the converse is true. She's almost saying that some of the dynamics follow from the symmetry. That's where I find this last sentence of Noether abstract is very profound. And I recommend people really to look at her paper and be wowed by how modern it is. And much more elaborate than any account of the paper in any textbooks.
Yeah. If I can go back to that very early historical period, people had thermodynamic arguments about why the photon should be quantized, why the electromagnetic field could be quantized. And because of these things that we're saying, the same arguments don't apply to the gravitational field. You can't isolate the gravitational field in any way. You can't keep it in a box. You can't thermalize it. And therefore, all of the analogy between thermodynamics and quantum systems, which led to the 1900s, 1910 versions of quantum mechanics, fail. You don't get anything from applying that kind of reasoning to gravity. So gravity departs from the rest of physics as far as at the very beginning of the first thermodynamic arguments about quantization.
Mm-hmm.
Christy, you had the last question.
Thank you. So there is another hope that that I find in the work you presented, and maybe this is too far-fetched. So following up your discussion with Hal Haggard about super selection sectors, one first obvious application is that if you want to have the degrees of freedom in a region to depend on the surface and not on the volume, obviously you need to reduce the Hilbert space that you normally would construct out of the region, and probably the super selection sectors can do this job. But the part that the other part that I'm optimistic about, which I say is maybe too early or too far-fetched to to think about it is that would it be possible that this super selection to reduce the possible Hilbert space so that the macroscopical appearance of the universe is what you observe? I mean, not presenting Schrodinger cats or Wigner friends or other superpositions like this.
Sure. That's very intriguing.
Yeah, no, I agree. Understanding the nature of the super selection sector and understanding dynamics as fusion of these superposition sectors. So time evolution is somehow through some kind of superposition of this super selection sector or transition.
In this case, I think maybe there would be a reason for interpretations like, so I would say not quite interpretations, but theories of quantum mechanics. And this, at this point, I don't necessarily mean quantum gravity, just in, trying to solve the measurement problem and the emergence of the classical level. So based only on unitary evolution without branching and without collapse or appearance of a collapse like in the pilot wave theory. There is this approach where you have only unitary evolution and only appears to be collapsing that was developed by Larry Schulman on the one hand, and a different version by Gerhard Toft, where he uses some discretization that he calls the cellular automaton interpretation. And I also try to do something in this direction. And I think if these super selection sectors reduce the Hilbert space so that the world appears macroscopically just like some classical or quasi-classical world, the way we see it, even if locally, I mean not locally, but on a smaller region, the entanglement is large enough, but maybe because of the region grows larger, the number of degrees of freedom decreases because it's only proportional with the area and not with the volume. I think maybe I think there is new hope for this kind of interpretation, but I don't know. I mean, maybe it's too early to say something.
Yeah, I don't know. I think what it's pointing towards is the fact that in such interpretations, maybe what is missing is this notion of decomposition into subsystems, which is somehow the notion of locality and how you kind of separate the notion of energy from the screening, the gravitational screening, right?
Yes.
And so it would be nice to have finite dimensional models that have these features built in and study the emergence of classicality from that. For instance, one thing it's saying is that if, usually it's assumed that, a state has to be typical in Hilbert space. And here I'm saying, no, in fact, a state has to be very atypical, and it's atypical in a very precise manner. So using that extra information should change a little bit this analysis, but I don't really have a concrete proposal.
Yes.
I think if you just study the system as a whole, I don't think there's any way you can talk about classicality, right? Classicality is more about understanding the relationship between different parts and formalizing that, in my view.
Yes. Thank you very much.
Great
talk. Great talk.
Thank you.
Maybe this is a good moment to wrap up.
Yeah, it's been 2 hours. So sorry, I hope it was accessible enough for people.
I think it was great. 2 hours is our usual. Okay. The talk will be available on YouTube. Yes, thank you very much, Laurent. Indeed, and hope to see you soon in Canada.
Thank you. Thank you.
Thank you.